There's a number science has already calculated, but almost no one has really stopped to think about what it means. 90% of all galaxies in the observable universe are invisible. Not theoretically invisible, not hidden behind dust clouds, but invisible in the most literal sense, measured, calculated, and confirmed by a 2016 study that analysed 20 years of data from the Hubble telescope. The old number was 200 billion galaxies. The accurate number is at least 2 trillion. That gap, 1.8 trillion galaxies, has never been directly observed by any telescope humanity has ever built. And in January 2025, the James Webb Space Telescope confirmed a galaxy that formed just 280 million years after the Big Bang. Its light has been travelling for 13.5 billion years to reach us. In every Hubble image ever taken of that region, it was pure black, nothing there. But it was always there. The night sky you see is not empty. It is the most densely occupied view you will ever face in your lifetime, and you cannot see a single thing in it. Why that happens is what we're going to explore together in today's video. As always, I'd love to know where in the world you're listening from and what time it is where you are right now. And don't forget to subscribe to Space Lull so you never miss our latest videos. But now, let's begin. Tonight, if you step outside and look up, what do you see? A few hundred stars maybe, a moon depending on the night, and surrounding all those points of light, darkness. A vast, quiet darkness stretching from one horizon to the other. The black of empty space, of nothingness. That feeling, the feeling of looking up and seeing infinite darkness, is one of the most universal experiences in human history. We have looked up at that night sky for 300,000 years. We have built mythology around it, philosophy around it, religion around it. And one consistent story running through every culture, every era. The universe is a vast, cold, nearly empty place, and we are a small, lonely speck of dust in some dark corner of it. That story feels true. It feels true because we can see the evidence of it every single night. The problem is, that evidence is wrong. Not wrong because someone made a measurement error, not wrong because technology wasn't advanced enough, though that's also true. Wrong in a deeper, more fundamental sense. The black you see when you look up at the night sky is not the black of cosmic space. It is the black of your own biological limitations. The human eye evolved in a very specific environment, the surface of a planet under the light of a star, over the course of a few million years. In that environment, what mattered was distinguishing ripe fruit from unripe, detecting movement in the undergrowth, recognizing familiar faces in dim light. The human eye was optimized for those tasks. The human eye was not optimized for cosmology. We perceive light within a very narrow band of wavelengths, roughly 380 to 700 nanometers. That is your entire window onto reality, no wider. And most of the light in the universe, the light from the oldest, most distant, most numerous galaxies, does not fall within that window. It falls in infrared, in microwaves, in radio waves. Wavelengths your eyes have no mechanism to detect, even as they arrive at your retina right now. Which means the night sky looks dark to you, not because the universe is dark. It looks dark because you are using the wrong instrument. But the real question isn't why our eyes are wrong. The real question is, why did it take more than 200 years for science to answer this? And the path to that answer is stranger than anything we could have imagined. In 1823, in the city of Bremen, Germany, a physician and amateur astronomer named Heinrich Wilhelm Olbers published a short paper. He wasn't proposing a new theory, he wasn't presenting new observational data. He was simply asking a question so disarmingly simple that no one could answer it. The question was this: if the universe is infinite, if it stretches on forever in every direction, and if it is filled with stars everywhere, then no matter which direction you look, your line of sight must eventually land on the surface of a star. Every single pixel of the sky should be blazing with light. The night sky should be a continuous wall of light, as bright and as hot as the surface of the sun. but it isn't. Try to picture this a different way. Imagine you are standing in a forest that extends infinitely in every direction. No edge, no boundary, just trees, and trees, and trees, forever, in every direction. No matter which way you turn, left, right, straight ahead, diagonally, your line of sight is eventually blocked by a trunk. There is no direction through which you can see past the forest. In the cosmic version of that forest, every tree is a star, and there is no direction in which your line of sight doesn't hit one. The night sky should be blinding in every direction, but it is dark. That is Olber's paradox, and what makes it an open wound in physics is not its complexity, but its simplicity. This is not a question that requires special instruments to recognize. It is present every night for anyone who looks up. A dark sky is direct, observable evidence that something is fundamentally wrong with our understanding of the universe. And for nearly a century, no one could explain why. The scientific community of the 19th century was not short on intelligence. This was the era of Maxwell, Kelvin, Helmholtz, minds that built the foundations of thermodynamics and electromagnetism. But Olber's paradox sat there like an accusation, unresolved, impossible to dismiss, impossible to ignore. It was the question everyone knew existed, and no one had an answer for. The first serious attempt to solve it came through a suspect that seemed entirely reasonable: dust. Perhaps, people reasoned, enormous clouds of interstellar dust were absorbing starlight before it could reach us. Like fog blocking headlights, space had its own fog, and that fog was darkening the sky. On the surface, this made perfect sense, but thermodynamics disagreed. And here is where physics became uncompromising. Anything that absorbs enough radiant energy must heat up, and anything that heats up to that degree begins to glow on its own. Those interstellar dust clouds, if they were absorbing the light of trillions of stars, would reach enormous temperatures and begin re-emitting energy as infrared radiation. The wavelength changes. The paradox doesn't go away. Dust was not the answer. The case went cold, and it stayed cold, quiet, frozen, unsolvable, for nearly 100 years, until the 20th century delivered 3 revolutions in physics, each more unsettling than the last, that finally broke it open. But the more frightening thing is, every answer only opened a larger question. Before we get to those revolutions, let's stay here for a moment, at the point where the case went cold, because there is something important hidden inside the failure of the dust theory. Not just that dust wasn't the answer, but why dust wasn't the answer, and what that tells us about how the universe actually works. Follow this chain of logic. Suppose space really is filled with interstellar dust, tiny clouds of particles scattered between the stars. Light from distant stars travels through space and strikes those dust particles. The dust absorbs the light, the sky grows darker, the paradox is solved. That's the reasoning, and on the surface it has no obvious flaw. The flaw lies in the next step, the step thermodynamics forces you to take. Energy does not disappear. This is one of the most fundamental laws in physics, the law of conservation of energy. When a dust particle absorbs a photon, the energy of that photon doesn't simply vanish, it is transferred into the particle. The particle heats up. Now multiply that by cosmic scales. If interstellar dust clouds are absorbing the light of trillions of stars, continuously, over billions of years, they would accumulate an enormous amount of energy. They would heat up, and any object hot enough to a certain degree will begin to emit radiation, not as visible light, but as infrared, as microwaves, as radio waves. Do you see the problem? Dust doesn't absorb light and hold it. Dust absorbs light and converts it. The energy is still there, just at a different wavelength. The sky is still saturated with energy. You simply need a different instrument to see it. And here is what's truly remarkable about this lesson. This wasn't a moment where science disproved a hypothesis with new observations. This was a moment where science disproved a hypothesis through pure reasoning. No new telescope needed. No new data. Just following the chain of logic all the way to the end. That is what the best physics so often does. not finding more facts, but thinking precisely enough about the facts already in hand. And that precise thinking closed the door on the dust theory and opened a void that no one could fill for nearly a century. Time passed. Great scientists came and went. Physics advanced in other directions: thermodynamics, electromagnetism, quantum mechanics in the early decades of the 20th century. But Olber's question remained, unresolved. Not forgotten, just waiting. Waiting until someone was brave enough, or perhaps naive enough, to propose what the entire scientific community considered unacceptable: that the universe might have a beginning. And that person was not a famous professor at a prestigious university. He was a priest. In 1927, at a scientific conference in Brussels, a young man stood before Albert Einstein and presented an idea. That man's name was Georges-Henri Joseph Edouard Lemaitre. He was 33 years old. He was a Belgian Catholic priest, wearing a clerical hat, dressed in black, and at the same time a PhD in astrophysics trained at MIT. He was not a prominent name in the scientific world. He held no position at a prestigious university. He was teaching at the Catholic University of Leuven, an institution that many of the world's leading physicists had never heard of. And the idea he was presenting before Einstein was something the entire scientific community considered nearly heretical. Lemaitre argued that the universe was not static, not eternal, not stretching on forever in both directions of time. He argued that the universe was expanding, that if you ran the film backward, everything would contract and contract and contract, down to a single point, a state of nearly infinite density and temperature, from which all matter, all energy, and space itself had erupted outward. He called it the primeval atom. The world would later call it the Big Bang. Einstein read the paper. He checked the mathematics. The mathematics were correct. Einstein could find no error in the calculations. But he turned to Lemaitre and said, in French, directly and without evasion, "Your mathematics are correct, but your physics is abominable." Einstein wanted an eternal universe, a universe with no beginning, no end, existing forever in a static state. He had even added a term to his own field equations, a completely arbitrary mathematical quantity with no physical basis, just to keep his theoretical universe from collapsing or expanding. He wanted the universe to stand still so badly that he was willing to alter his own equations to force it. But the real universe did not cooperate with Einstein's wishes. 2 years later, in 1929, Edwin Hubble published observational data that confirmed precisely what Lemaitre had calculated from pure theory. Galaxies were receding from one another. Space was expanding. The universe was not static. Einstein admitted the error. He later called his cosmological constant the greatest blunder of my life. Lemaitre was right. A 33-year-old Belgian priest teaching at a university Einstein had never heard of, right about the nature of the universe when Einstein was wrong. But what matters more is the consequence of being right. If the universe is expanding, if everything is moving away from everything else, then when you run the film backward, everything must converge. The universe has a beginning. It did not exist forever in the past. It has an age. And that age, a specific number, measured with astonishing precision, is the first key to unlocking Olber's paradox. But that key is more complicated than it appears, and to understand why, you need to know just how precise that number is, and what it truly means. The universe is 13.8 billion years old. That is not a rough estimate, not a rounded number for easy remembering. It is one of the most precisely measured quantities in all of physics, pinned down to within about 40 million years by the European Space Agency's Planck satellite, through measurements of the cosmic microwave background radiation at unprecedented resolution. 40 million years sounds like a large margin of error, but put it in context, that is an uncertainty of 0.3% across 13.8 billion years. We know the age of the universe more precisely than we know the age of most geological structures on Earth. And that number, 13.8 billion years, carries a physical consequence that cannot be avoided, and that shatters the entire foundation of Olber's paradox. Light travels at a finite speed, 299,792 kilometers per second, not infinite, not instantaneous. Finite, a specific number, measured with such precision that it now serves as the basis for the official definition of the meter in the International System of Units. And that finite speed, combined with the finite age of the universe, creates a hard limit on how far we can see. Follow this logic slowly. If the universe is 13.8 billion years old, and light travels at 299,792 kilometers per second, then the farthest light that could possibly have reached us is light that has been traveling for 13.8 billion years since the Big Bang. Any galaxy at a greater distance than that, any galaxy whose light needs more than 13.8 billion years to arrive, that light has not reached us yet. Those photons exist. They are moving. They have been moving since before the Earth was formed, but right now, in this very moment as you are listening to these words, they are not here. They are in transit, and until they arrive, they do not exist in our sky. This creates what cosmologists call the observable universe, a sphere roughly 93 billion light-years in diameter, centered on wherever you happen to be standing, beyond which you are permanently and structurally blind. Not because there is nothing there, but because the universe's messaging system, light, has not had enough time to deliver the messages from places that far away. Notice I said 93 billion light-years, not 13.8 billion. The larger number is because space itself has been expanding throughout the time that light has been travelling, pushing the most distant galaxies farther than the distance their light has actually crossed. And here is the part that makes everything genuinely unsettling. That observational horizon, that boundary of the observable universe, is not a limit we haven't reached yet. It is a limit we will never reach. Because it is receding away from us at the speed of light, not because anything is moving, but because the space between us and that horizon is generating new space faster than light can cross it. We are standing inside a bubble. That bubble is growing, but its edge always remains just out of reach, not because of any lack of technology, but because the nature of space-time does not permit anything to cross it. Anything that exists outside that bubble will forever remain beyond our knowledge, not because we lack ambition, but because the structure of reality makes it physically impossible. And that bubble, 93 billion light-years in diameter, contains roughly 2 trillion galaxies. If the full universe is 250 times larger than the observable part, that is 500 quadrillion galaxies. If it is infinite, the number is meaningless. Just galaxies in every direction, without end. We cannot distinguish between these possibilities with current physics. That is not a poetic mystery. That is a technical limitation we do not know how to solve. Let's pause here for a moment, because this is the point where most explanations of Olber's paradox stop and say, all right, the universe has a finite age, problem solved. But it isn't solved, not completely, and the unsolved part is the part that is genuinely disturbing. Think about this. Even within our observable universe, that bubble 93 billion light-years across, there are 2 trillion galaxies, each containing hundreds of billions of stars. If light from all those stars is reaching us, the sky should still be measurably brighter than what we actually see. The age of the universe explains some of the darkness, not all of it. Something else is killing the light. And this is where physics becomes genuinely uncomfortable. When Hubble confirmed that galaxies were receding from one another, that space was expanding, he had inadvertently revealed a second mechanism, completely independent of the universe's age, that was pushing the sky into darkness. Follow this carefully. A photon leaves a distant galaxy heading toward Earth. It enters the expanding space between that galaxy and us. As the photon moves, the space it is travelling through is stretching, and the light wave stretches with it. The wavelength increases, the frequency drops, the energy decreases. A photon that left as blue light may arrive as red light. A photon that left as visible light may arrive as infrared. And a photon from a galaxy far enough away, one whose light has been travelling for, say, 10 billion years, its entire visible spectrum gets pushed into infrared. That galaxy vanishes completely from optical telescopes, Not because the telescope isn't powerful enough, but because the light is no longer light, at least not the kind any optical instrument was designed to receive. Now think about the cosmic horizon in this context. Even within our 93 billion light-year observable bubble, the galaxies near the edge of the horizon, those whose light has been travelling for close to 13.8 billion years, have their entire visible spectrum shifted out of the optical range. Your eyes cannot see them. Optical telescopes cannot see them. They are broadcasting a signal, but that signal is speaking a language every optical instrument we have cannot hear. And the cosmic horizon is not a boundary you could reach if you just travelled far enough. It is a boundary that is actively retreating from you. In this very moment, as you are listening, the observational horizon is receding from us at a speed exceeding the speed of light. Not because anything is moving faster than light, but because the space between us and that horizon is generating new space faster than light can cross it. This is something no analogy can fully capture. The horizon is not a wall we haven't reached. It is a wall running away from us at the speed of light. We will never touch it. We will never see past it. Whatever exists beyond it, whether that is 250 times more galaxies, or countless galaxies without end, or something we have no concept of yet, will forever remain outside our knowledge, not because we lack ambition or technology, but because the structure of space-time makes it physically impossible. So we have two reasons now, the age of the universe and the expansion of space, and together they still do not fully explain the darkness of the night sky. Because even accounting for both, the sky should still be brighter than what our eyes see. The third reason lies hidden in a simpler question. How many galaxies have we actually counted in the observable universe? The answer, it turns out, was wrong in a way that is staggering. And the evidence came from one man's decision at one observatory in December 1995. A decision his colleagues openly called a waste of valuable telescope time. To understand why we miscounted the galaxies in the universe, and how, we need to go back to 1929 at the Mount Wilson Observatory on the hills above Los Angeles, California. Edwin Hubble was working with the 100-inch Hooker reflecting telescope, at the time the largest optical telescope in the world. He was measuring the spectra of distant galaxies, splitting the light from each galaxy into its component wavelengths, producing a band of colour with distinctive bright and dark lines. Those lines were chemical fingerprints. Each element emits and absorbs light at specific, unique wavelengths. Hydrogen looks different from helium. Helium looks different from oxygen. Oxygen looks different from iron. When you look at the spectrum of a star or galaxy, you can identify the elements present by the precise positions of those lines. Hubble noticed something strange. For distant galaxies, those familiar fingerprint lines appeared in the wrong position, shifted toward longer wavelengths, toward the red end of the spectrum. And when he measured the distances to those galaxies and plotted the degree of redshift against distance, he found a perfectly linear relationship. The farther the galaxy, the more its light was shifted toward the red. Not random, not noise, not measurement error, a systematic, universal pattern applying to every galaxy he measured. The most popular explanation at the time was that galaxies were flying away from us, like the way a train whistle drops in pitch as the train departs. But that interpretation had a problem. It implied the Milky Way sat at the centre of the universe, with everything flying outward from us in every direction. And that contradicted every principle Copernicus had established since the 16th century, that we are not the centre of anything. The correct interpretation, built on Lemaitre's theoretical work, was this. Galaxies are not flying through space. Space itself is stretching. The fabric of the universe is expanding, carrying everything with it, like dots of paint on the surface of a balloon being inflated. No dot moves across the rubber. The rubber between every pair of dots is stretching, and every dot sees every other dot moving away, not because any dot is moving, but because the distance between them is growing. That means there is no centre, no point in the universe more special than any other. From any galaxy, every other galaxy looks like it is receding, and the farther the galaxy, the faster it appears to recede, not because it is moving faster, but because there is more expanding space between you and it. Now think about what that does to light. A photon leaves a distant galaxy heading toward Earth. Throughout its journey, possibly many billions of years, the space it is moving through is continuously expanding, and the light wave stretches with that space. The wavelength grows, the color shifts, the energy drops. This is not a small effect. Given enough time and enough distance, it completely transforms the nature of the light. And you know what's remarkable? The first time we discovered the most direct evidence of this process, no one realized what it was. They thought it was equipment noise. They thought it was pigeon droppings. Let's follow the journey of one specific photon, not an abstract photon, a real one, a single particle of light emitted by a star in a galaxy 10 billion light-years away, around 3.8 billion years after the Big Bang. At that moment, Earth did not exist. Our solar system did not exist. The material that would eventually become the Sun and its planets was still scattered through interstellar gas clouds. That photon was released at a wavelength of roughly 500 nanometers, pale green light, right in the middle of the human visible range. If you could have stood beside that star at that moment and looked toward where Earth would exist 3.8 billion years in the future, you would have seen that photon departing at the speed of light, heading toward you across time. Now follow what happens to it. In the first 5 billion years of its journey, the expansion of space had stretched its wavelength from 500 nanometers to roughly 650 nanometers. It was no longer green, it had become red light, still within the visible range, but shifted significantly. After 10 billion years, the wavelength had grown beyond 1,000 nanometers. It had crossed the boundary of visible light and entered near-infrared. Human eyes can no longer detect it. Standard optical telescopes cannot see it. But specially designed infrared cameras, like the instruments on the James Webb Space Telescope, can. Now consider the more extreme case. Around 380,000 years after the Big Bang, the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms for the first time. Before that point, the universe was a dense, opaque plasma. Light could not travel freely because it was constantly being scattered by free electrons. But when atoms formed, the universe suddenly became transparent. Light could move freely for the first time, and the universe was blazing at that moment. A temperature of roughly 3,000 Kelvin, comparable to the surface of a red dwarf star, far hotter than molten iron. That light radiated in every direction, filling the entire universe. That was 13.8 billion years ago. In the 13.8 billion years since, the universe has expanded by a factor of roughly 1,100, and the wavelength of that light has been stretched by the same factor. Light that began at around 1,000 nanometers, near infrared, has been pulled to about 1.1 millimeters. That is the microwave region of the electromagnetic spectrum. Its effective temperature has dropped from 3,000 Kelvin to 2.725 Kelvin, just over 2.5 degrees above absolute zero. Colder than anything that exists naturally on the surface of Earth. Colder than the coldest recorded temperature in Antarctica. Colder than every mountain peak, every desert at night, every deep ocean trench. The first light of the universe, brighter than molten iron, had been slowly executed by the expansion of space over 13.8 billion years until it became a cold, faint microwave whisper, filling every cubic centimeter of space. And we detected it, not because we knew we were looking for it, but because it refused to disappear when we tried to eliminate what we thought was equipment noise. This is where the story of physics collides with reality in the most unexpected way possible. And what is more frightening is this. What Penzias and Wilson found in their antenna was not an exception. It is the rule. Every photon from every distant galaxy is on the same path of slow execution, being stretched, cooled, pushed out of the range human eyes can detect. Space is performing a slow, patient execution on every photon that travels through it. The greater the distance, the greater the stretching. The greater the stretching, the less energy the photon carries when it arrives. A galaxy at the edge of the observable universe, one whose light has traveled more than 13 billion years, its visible light arrives here as mid-infrared radiation. You need a space telescope cooled to near absolute zero to detect it. Your eyes register an ocean of 13 billion-year-old light as absolute darkness. In 1964, at Bell Telephone Laboratories in Holmdel, New Jersey, two physicists named Arno Penzias and Robert Wilson were preparing a large horn antenna for satellite communications. That antenna, a 6-meter metal structure shaped like a sharp horn, had originally been built to communicate with Bell's Telstar satellite. But by 1964, Telstar had been superseded by better technology, and Penzias and Wilson had the opportunity to use it for radio astronomy research. They began calibrating the equipment and immediately ran into a problem. There was a persistent background noise they could not eliminate. It came from every direction equally. It did not change with the seasons. It did not change with the time of day. It did not change no matter where the antenna was pointed. It was simply there, a steady, even, inexplicable hiss at a wavelength of roughly 7.35 centimeters. Penzias and Wilson began systematically ruling out every possible source. Electronic interference from nearby New York City? They checked. Not that. Because the noise came from every direction, including away from the city. Atmospheric nuclear testing? They calculated. The levels didn't match. Interference from the equipment itself? They disassembled and inspected every component, replacing and recalibrating each part. And during their inspection of the antenna, they found something unexpected inside the horn. A pair of pigeons had nested there, leaving what Penzias later described in technical terms as white dielectric material, which is to say, pigeon droppings. They removed the birds. They cleaned the antenna. They continued measuring. The noise was still there, because it wasn't noise. Around the same time, about 60 kilometers from Holmdel, at Princeton University, a group of theoretical physicists led by Robert Dicke was preparing to build a device to search for exactly the signal that Penzias and Wilson were trying to eliminate. Dicke had calculated that if the universe truly began from an extremely hot and dense state, the light from that period must still exist, cooled and stretched by 13.8 billion years of cosmic expansion into a faint microwave radiation filling the entire sky. When Penzias happened to call an acquaintance at Princeton and described the strange noise, the Princeton group understood immediately. They had been beaten to the finish line. Penzias and Wilson had found what Princeton was preparing to search for. The noise that would not go away was the cosmic microwave background radiation, the afterglow of creation, the first light of the universe, released when the universe first became transparent, around 380,000 years after the Big Bang, stretched across the entire age of the cosmos into a uniform microwave whisper filling every cubic centimeter of space, arriving from every direction in every moment. Its temperature? 2.725 Kelvin. Uniform to 1 part in 10,000, one of the most even distributions ever measured in nature. Penzias and Wilson published their discovery in 1965. They received the Nobel Prize in Physics in 1978 for a discovery they had initially mistaken for pigeon droppings. But the true significance of the cosmic microwave background goes far beyond the Nobel Prize. It is direct, measurable, irrefutable evidence that the universe began from an extraordinarily hot and dense state, and that the expansion of space over 13.8 billion years has transformed that light from brighter than molten iron into colder than anything that exists naturally on the surface of Earth. And that transformation, that slow execution, is not ancient history. It is happening right now to the light from every distant galaxy in the observable universe. In every second you exist, trillions of photons from distant galaxies are arriving at your location, stretched, cooled, pushed out of the range your eyes can detect. They are touching you right now. You simply cannot feel them. So we have two reasons, and together they are still not enough to explain the full darkness of the night sky. The third reason is hidden inside a photograph. A photograph one man staked his reputation on taking by looking at something everyone around him insisted held nothing at all. In December 1995, in Baltimore, Maryland, the director of the Space Telescope Science Institute, a man named Robert Williams, made a decision many of his colleagues simply could not understand. He held access to the Hubble Space Telescope, the most powerful optical instrument humanity had ever placed in orbit, developed and launched at a cost of nearly $2.5 billion, with an observation queue backed up by years of requests from astronomers across the world. Every hour of Hubble time was so scarce that research proposals went through months of intensive review before being approved, and Williams had decided to spend 10 consecutive days of that observation time, roughly 150 orbits of Hubble around the Earth, staring at a completely blank patch of sky near the constellation Ursa Major. There were no bright stars in that region, no nearby known galaxies close enough for detailed study, no interesting light sources recorded by any previous observation, just a dark, featureless patch of sky, chosen partly because of its emptiness, to avoid contamination from nearby bright objects. Williams's colleagues did not stay quiet about their skepticism. Some openly said this was a waste of telescope time, that there was nothing there to see, that this precious resource should be reserved for known targets, well-defined questions, light sources that astronomers already had specific reasons to find interesting. Williams proceeded anyway. He was the institute director. He had the authority to allocate a portion of the observation time at his own discretion, and he had decided that looking into nothing, looking long and deep into a patch of sky with nothing in it, was worth doing. The result of those 10 days of observation, an image composited from 342 individual exposures, was published in January 1996 and almost immediately became one of the most important photographs in the history of science. The Hubble Deep Field contained approximately 3,000 galaxies, in a patch of sky so small that if you held a 1 millimeter grain of sand at arm's length, it would cover the entire area. A patch that had looked completely empty, and it held 3,000 galaxies, some of them among the most distant objects ever observed at that time, their light having travelled more than 10 billion years. The astronomical community went silent for a moment, then understood the implications. If a random blank patch of sky contained 3,000 galaxies, and that patch represented a tiny fraction of the full sky, then scaling that number across the entire sky gave a total galaxy count in the observable universe of roughly 100 to 200 billion. That number, 100 to 200 billion galaxies, became the standard figure, cited in textbooks, repeated in popular science, taught in astronomy classes around the world. For nearly 20 years, it was the best answer science had to the question, how many galaxies are in the observable universe? In 2004, they repeated the experiment with longer exposures, pointing toward the constellation Fornax in the south. The Hubble ultra-deep field contained roughly 10,000 galaxies in an even smaller area, some of them among the most distant objects ever seen, their light having travelled more than 13 billion years. Every time they looked harder at a dark patch, they found it fuller. Every time they increased the exposure time, more galaxies emerged from the darkness. But there was something those images, however remarkable, could not capture. And that is what a team of astronomers in Nottingham, England, finally quantified in 2016. And when they did, they changed completely our understanding of the true scale of the universe. The 200 billion figure was wrong. Wrong by a factor that even those who discovered it had to pause and absorb the full meaning of. Christopher Consolis was not the first person to doubt the 200 billion figure. For years, astronomers had been aware that Hubble, however powerful, had a detection flaw. There were galaxies too faint, too small, too distant to register on its detectors. Their light reached Hubble, but it was too weak to distinguish from the random noise of the instruments. They knew 200 billion was an undercount, a baseline, not a true total, but no one knew by how much. Until Consolis and his team at the University of Nottingham decided to find the answer using a method no one had tried at this scale before. Instead of simply counting what we can see, build mathematical models of what we cannot see. Consolis' team spent years analysing data from the deepest galaxy surveys available, the Hubble Deep Field, the Hubble Ultra Deep Field, and others. They were not just counting visible galaxies, they were studying how galaxy density changed across cosmic time, how the number of galaxies per unit of volume shifted as you looked back toward increasingly distant cosmic eras. And what they found in that data was a clear, consistent pattern. The early universe contained significantly more small galaxies than what we see today. Not just a little more by a large factor, and most of them were too small and too faint for Hubble to detect. Here is what you need to understand about the early universe. It was an entirely different environment. When the universe was 1 to 2 billion years old, it was packed with small, dim, irregular galaxies, messy clumps of matter, clouds of stars without clear structure, nothing like the elegant spirals and massive ellipticals we see in the nearby universe today. Those large structures didn't arrive fully formed. They were assembled piece by piece over billions of years, through countless collisions, mergers, and the consumption of smaller galaxies by larger ones. Our Milky Way is a prime example. We tend to think of the Milky Way as home, a stable, elegant spiral structure with 200 to 400 billion stars organised into spiral arms around a central core. But the Milky Way we see today is not the original Milky Way. It is the product of billions of years of consumption. Astronomers have identified at least 60 smaller galaxies, or their remnants, that the Milky Way has absorbed throughout its history. The Canis Major dwarf galaxy, discovered in 2003, is currently being stretched apart by the Milky Way's tidal forces, its stars dissolving into the galactic disk. The Sagittarius dwarf galaxy, a compact galaxy roughly 1/100th the mass of the Milky Way, is being torn apart right now, its stars being drawn out into long streams that wrap around the Milky Way. Not in the distant future, not in the geological past. Right now, in the moment you are reading these words, the Milky Way is consuming another galaxy. And the small galaxies that were not consumed, those that survived intact in the distant universe, most of them sit below Hubble's detection floor. They exist. They have mass. They contain stars. Some of them have planets, but their light, after travelling to Earth across billions of years of cosmic expansion, is too weak to separate from the random noise of the best astronomical detectors we had before James Webb. When Consolis and his team combined all these factors, the density trend of galaxies across cosmic time, the missing population of small galaxies, Hubble's detection limits, the number they arrived at was not 200 billion, it was at least 2 trillion. 10 times more. Not 10% more, not double, 10 times. And that, at least, matters. It is the lower bound of the estimate, not the true total, because there are still other categories of faint galaxies that even their models may have missed. 90% of all galaxies in the observable universe have never been directly observed by any telescope. They are not absent from reality, they are absent from our data. And the difference between those two things is the difference between what the universe actually is and what we can prove about it. The James Webb Space Telescope was designed specifically to begin closing that gap. To understand why James Webb is a qualitative leap forward, not simply a more powerful Hubble, you need to understand the fundamental problem it was designed to solve. Hubble is an optical telescope. It collects light in the visible range and near infrared. Essentially a modest extension of what the human eye can see. For nearby and moderately distant galaxies, that is entirely sufficient. But for the most ancient galaxies, those that formed when the universe was only a few 100 million years old, their light has been stretched by cosmic expansion completely out of the range Hubble can detect. They broadcast in mid-infrared and far infrared, wavelengths that Hubble is essentially blind to. James Webb was designed from the start to see exactly those wavelengths. Its primary mirror, a honeycomb structure of 18 hexagonal segments, 6.5 meters across in total, is coated in a thin layer of gold. Not for aesthetics, but because gold is the best reflective material for infrared light among metals that can practically be used in space. Each segment can be adjusted to a precision of 1/10,000th the diameter of a human hair, so that all 18 segments function as a single, perfect mirror. But a large mirror is not enough. The larger problem is heat. Any object above absolute zero emits infrared radiation. You emit infrared. The telescope emits infrared. And if the telescope is trying to detect extremely faint infrared signals from 13 billion-year-old galaxies, the infrared radiation from the telescope itself would completely drown those signals out. Like trying to hear a whisper from the next room or someone is screaming directly into your ear. The solution is to cool the entire science side of the telescope, the mirror, the instruments, the detectors, to extreme temperatures. James Webb achieves this in two ways: a passive sun shield the size of a tennis court, 5 layers of hair-thin polyimide membrane coated in aluminium and silicon, stacked with gaps between layers to radiate heat into space, keeps the cold side of the telescope at around -233 degrees Celsius. And to cool the mid-infrared imaging instrument, MIRI, down to its operating temperature, -266 degrees Celsius, just 7 degrees above absolute zero, Webb uses an electrically powered mechanical cooling system. At -266 degrees Celsius, thermal radiation from the telescope itself is nearly zero, and the faint infrared signals from ancient galaxies, signals that Hubble could not separate from background noise, become detectable. Webb launched on December 25, 2021. After 6 months of calibration in space, an extraordinarily complex process involving aligning 18 mirror segments to nanometer precision, it began collecting scientific data. What it found shook the field. In its first months of operation alone, Webb detected candidate galaxies forming just 300 to 400 million years after the Big Bang, when the universe was barely 3% of its current age. These galaxies were not just earlier than predicted, they were larger and more structurally complex than anything the standard theoretical models said should be possible at that point in cosmic history. The lambda-CDM model, the standard cosmological model describing how matter clusters and structures form after the Big Bang, stated clearly that there was not enough time for matter to collapse, cool, and organize into large galaxy-scale structures like what Webb was seeing at that epoch. The data said the model was wrong. And here is what you need to understand about good science. That did not cause panic. It caused excitement. Because a model that doesn't match the data is not a failure. It is an opportunity. It means reality is telling us something we have not yet understood, and that is a chance to understand more deeply. But to understand more deeply, you need more precise data. You need not just to see those galaxies, you need to measure their distances exactly, to confirm spectroscopically that they are truly where they appear to be. And that is what happened in 2024, with a galaxy whose name is almost impossible to pronounce, but whose meaning is impossible to forget. Its name is JADES-GS-Z14-O. JADES stands for JWST, Advanced Deep Extragalactic Survey, the deepest extragalactic survey ever conducted by James Webb. GS stands for Goods-South, the region of sky where it was found. Z14 indicates its redshift, the degree to which its light has been shifted toward red, at a value of 14.32. And the 0 at the end is because it was the first object confirmed at that redshift in the survey. What does a redshift of 14.32 mean? It means the light from this galaxy was emitted when the universe was roughly 15 times smaller than it is today in linear terms. Or in other words, when the universe was only about 1/3375th of its current volume. It means that light left the galaxy approximately 290 million years after the Big Bang, when the universe was just 2% of its current age. And it means that light has been travelling for 13.5 billion years to reach our telescope. 13.5 billion years. More than 3 times the age of the Earth. Nearly equal to the entire age of the universe. In October 2023, the JADES team conducted deep imaging of the field, building confidence that JADES-GS-Z14-O was an extremely distant galaxy candidate. Then in January 2024, Webb used its NIR SPEC instrument to observe the galaxy for nearly 10 hours. The spectroscopic data came back unambiguous. JADES-GS-Z14-O was confirmed at a redshift of 14.32, truly formed around 290 million years after the Big Bang. No longer a candidate. The most distant object ever confirmed spectroscopically in the history of astronomy. The result was published in Nature, the most prestigious scientific journal in the world, by a collaboration of more than 80 researchers from multiple institutions across multiple countries. Not a fringe claim from a small group with unverified methods. Results as rigorously reviewed as anything modern science is capable of. And those results presented a serious problem for standard cosmology. JADES-GS-Z14-0 does not just exist at 290 million years after the Big Bang, that alone is remarkable. It is also significantly larger and chemically more complex than anything the lambda CDM model predicted should be possible at that point. This galaxy contains evidence of oxygen, a heavy element produced only inside stars through nuclear fusion, and dispersed into interstellar space only when those stars explode as supernovae. That means by the time the universe was just 290 million years old, this galaxy had already had enough time to produce multiple generations of stars. Stars forming from primordial hydrogen and helium, living long enough to synthesize heavier elements, dying in supernova explosions that enrich the interstellar gas, and then a new generation of stars forming from that enriched gas. All of that, multiple generations of stars, their complete life cycles, within the first 290 million years of the universe. The standard model did not predict that was possible. Theorists are exploring several possible explanations. Some propose that the rate of star formation in the early universe was significantly faster than our simulations predict, that the initial conditions allowed gas to collapse into stars far more efficiently. Others suggest that post-Big Bang initial conditions produced more concentrated pockets of dense matter in certain regions, allowing structures to form more rapidly. A smaller group is questioning whether the lambda CDM model requires more fundamental revision, whether something in our understanding of dark matter, dark energy, or cosmic inflation itself is inaccurate. Those are three different conversations, all still ongoing, none resolved. And in every Hubble image ever taken of the region of sky where JADES-GS-Z14-0 exists, it was pure black. No signal, no hint, just the darkness that Hubble could not see past. Webb sees it everywhere it points. And here is what is truly worth pausing to consider. The 2 trillion galaxy figure, the number that replaced 200 billion, only accounts for galaxies that exist within our observable universe. That 93 billion light-year bubble. What exists beyond the cosmic horizon, in the part of the universe whose light has not had time to reach us, is not counted, cannot be counted. There is no theoretical upper limit on that number, because we still do not know how large the full universe actually is. Darkness has never been evidence of absence. It is a mask. And it took 200 years, 2 of the most expensive instruments humans have ever built, and thousands of scientists working across generations to begin pulling it down. We have travelled a long way. From Heinrich Olbers and his uncomfortably simple question in 1823, through Georges Lemaitre and his confrontation with Einstein, through Edwin Hubble and the moment he realised space was expanding, through Penzias and Wilson and the noise that wouldn't go away, the one that turned out to be the afterglow of creation, through Robert Williams and 10 days of staring into nothing, through Christopher Consolis and the recensus of the entire universe, through James Webb and the galaxies that weren't supposed to exist. And now, after all of that, we can look back at the original question and see it as something completely different. Why is the night sky dark? The answer is not one reason. It is 3 reasons operating simultaneously. 3 independent mechanisms, each astonishing in its own right, all converging to produce the same result. A sky that a species evolved on a small planet reads as empty, while in reality it is saturated in ways biology has no means of detecting. The first reason: the universe has an age. 13.8 billion years, not infinite, not eternal, but a specific, finite span of time, measured with a precision that few physical quantities can match. That age creates a horizon, a hard boundary defined by the speed of light and how long the universe has existed. Light from galaxies beyond that horizon has not arrived, and will not arrive within the remaining lifetime of our Sun. Not because there is nothing there, but because the universe's messaging system, light, has not had time to deliver the messages from those places. We are locked inside a bubble of visibility, not by technology or ambition, but by the fundamental structure of space-time. And that wall is receding from us at the speed of light. We will never reach it. Whatever exists on the other side, whether 250 times more observable universe or an endless number without conclusion, will forever remain outside our knowledge. That is not a poetic mystery. That is a physical fact that cannot be changed. The second reason, the expansion of space is performing a slow execution on every photon that moves through it. Light from distant galaxies is being stretched, from visible to infrared, from infrared to microwave, from microwave to radio. Every step of stretching is a step away from the 380 to 700 nanometer range the human eye can detect, and every step is a step away from the perceptual capacity of every creature that has ever evolved on this planet. Because no living thing in the history of life on Earth has ever needed to detect infrared from 10 billion-year-old galaxies to survive. The sky is not dark. It is saturated with ancient light. But that ancient light has been stretched to the point where it is functionally invisible to every biological sensor evolution has ever produced on this planet. We are the wrong instrument. And no amount of training or practice can change that. Because this is not a skill limitation. This is a biological limit encoded into the structure of the retina, into the chemistry of cone and rod cells, into the architecture of the visual cortex. The third reason, most of the galaxies in the observable universe are too faint, too small, and too ancient to register on the best instruments we had before James Webb. 2 trillion galaxies, and 90% of them are ghosts. Present in reality, absent from our data. Broadcasting signals so weak they drown in the background noise of the very instruments we use to search for them. 3 mechanisms, 3 layers of understanding, all operating at once, all producing the same result. But what is more disturbing than any of those mechanisms is what they imply when placed beside each other, what they say about the nature of what we can know, what we cannot know, and how wide the gap between those two things actually is. And that leads to a question science alone cannot answer, the question of what all of this means for how we think about our place in the universe. On February 14, 1990, the Voyager 1 spacecraft was 6.4 billion kilometers from Earth, farther than any human-made vessel had ever traveled at that point, having passed the orbit of Neptune and heading into interstellar space. The astronomer Carl Sagan had persuaded NASA, after years of advocacy, to turn Voyager 1's camera back toward the Sun and photograph the solar system from that distance. This was not an obvious decision. Pointing the camera toward the Sun risked damaging it, and in strictly scientific terms, the image would yield no useful new data. Voyager had long since completed its primary scientific mission. But Sagan did not want scientific data. He wanted a photograph. In the resulting image, a mosaic of 60 individual frames, Earth appeared as a pale, bluish point of light, suspended in a scattered ray of sunlight. Less than a single pixel, no distinguishing features, no sign of continents or oceans, just a point, like thousands of other points in the same image, except that this one was the home of everyone who had ever lived, everyone alive now, and everyone who would ever live in any imaginable future. Sagan named the photograph the pale blue dot, and in his most famous speech, he pointed to it and said, "Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on a mote of dust suspended in a sunbeam." The black background behind the pale blue dot gave that message its weight. The vast emptiness surrounding that tiny point was the visual proof of our smallness and solitude. That is why the photograph works as an existential argument. That is why it stops people. But that black background is wrong. Not wrong in the sense that anyone falsified the photograph. The image is entirely accurate. It records exactly what Voyager's camera detected on February 14th, 1990. But what Voyager's camera detected and what was actually there are two profoundly different things. The darkness behind the pale blue dot is not empty. It is filled with things that Voyager's camera, designed to photograph planets in sunlight, could not detect. Infrared light from trillions of galaxies, microwave radiation from the early universe, radio signals from quasars and pulsars, and hidden within all those wavelengths is the evidence of a universe that is not empty at all, a universe saturated in ways no optical camera can capture. In every region of the black sky behind that pale point, every stretch of darkness that Sagan pointed to as evidence of vastness and loneliness, there are thousands of galaxies, each containing hundreds of billions of stars. Many of those stars with planetary systems, a fraction of those systems with planets in habitable zones, not too hot, not too cold, with conditions that allow liquid water to exist on the surface. The darkness that made us feel small and alone was never evidence of solitude. It was evidence of instrument limitations. And that instrument was not Voyager's camera. It was the human eye, the human brain, the entire sensory and information processing system of a species that evolved in a very narrow ecological niche on a very specific planet. Sagan was not wrong about the photograph. He was wrong about the meaning of the black background. And that is not a criticism of Sagan. He was a great man, and the pale blue dot remains one of the most powerful arguments ever made for peace and human humility. But there is a deeper layer of understanding that the science of the decades after his death has revealed, a layer he did not have the data to see in 1990. We are not alone in the void. We have never been alone in the void. We have always been surrounded by the light of trillions of galaxies arriving at our position every second, by radiation from the early universe filling every cubic centimetre of space, by signals from sources we have not yet built instruments to hear. What changed is not the universe. The universe has always been this way. What changed is us. We built instruments good enough to begin hearing what has always been speaking to us. And that leads to one final thought, one that in some ways is the most astonishing thing in this entire story. Imagine that someone, through some kind of magic or some surgical procedure that doesn't yet exist, replaced your retinas with infrared sensors. Not sensors slightly better than human eyes, but sensors operating in the wavelength range that the oldest, most distant, most numerous galaxies in the observable universe are broadcasting in by the time their light finally arrives on Earth after billions of years of travel. Step outside on a dark night. Look up. The sky will not be dark. It will be a continuous wall of light from horizon to horizon. Not a single dark point, not a single gap, not one region of sky without a light source. Every direction saturated, every point on the sky occupied, not by nearby stars, they are still there, but they would be overwhelmed, but by the infrared light of trillions of galaxies whose light has travelled for billions of years and arrived here shifted out of the visible range into exactly the band your new eyes can detect. The sky would look like the inside of a furnace, not metaphorically, in the direct physical sense. If you could see all the electromagnetic radiation arriving at your location from every direction, across every wavelength combined, the sky would be a continuous wall of energy with no dark point anywhere. But you don't have those eyes. No one on this planet does. No creature in the entire history of life on Earth, not a single bacterium, not a shark, not an eagle with vision 8 times sharper than a human's, has ever evolved the mechanism to detect infrared from distant galaxies. Because there was no evolutionary pressure to do so. There is no survival advantage in seeing infrared from a far galaxy. Evolution does not know about and does not care about cosmology. Evolution cares about living long enough to reproduce, and to do that on the surface of Earth, under the light of a G2-type star. You need to detect wavelengths of roughly 380 to 700 nanometers. That is the range the sun emits most strongly. That is the range plants reflect in ways useful for distinguishing ripe from unripe fruit. That is the range where skin tones and facial expressions become clearest. That range, 380 to 700 nanometers, is your entire window onto reality. And the cosmological fact is, that window has been calibrated beautifully to miss most of what exists in the universe. Not most, the vast majority. Light from the observable universe is distributed across the entire electromagnetic spectrum, from gamma rays to radio waves, spanning billions of wavelengths. Your visible range, 380 to 700 nanometers, is a band so narrow that if you drew the entire electromagnetic spectrum on a ruler stretching from Earth to the Moon, your visible range would be about 1 millimeter wide. 1 millimeter. On a ruler 384,000 kilometers long. That is what your eyes can detect. That is the entirety of reality that biology has granted you access to. And the darkness you see when you look up at the night sky, the vast, quiet black spreading from horizon to horizon, is the sum of everything that lies outside that 1 millimeter on that ruler. It is not emptiness. It is everything reality contains that you are not equipped to see. But here is the remarkable thing, the thing that in some ways is the most astonishing part of this entire story. We built instruments that can see it, not human eyes, but silicon detectors, gold-coated mirrors, mechanical cooling systems, signal processing computers, noise reduction algorithms, networks of scientists across the world working together to transform raw data into images the human brain can process. We have built a workaround for our own biological limitations. We cannot see infrared with our eyes, but we can build instruments that see it for us, and then convert what they see into images we can understand. James Webb is the current pinnacle of that workaround, and what it is finding in the darkness, galaxies that weren't supposed to exist, structures too large and too early, mysteries that our standard models cannot yet explain, is a map being drawn piece by piece of a reality far larger than anything we can see with the naked eye. The dark sky is not evidence of absence. It is a map of the age of the universe, the expansion of space, the limits of biology, and the sheer scale of what exists beyond our sight. And that map is saying something very simple. You are not alone in the void. You never were. It's just that no one had yet built the instrument powerful enough for you to see everything that is out there with you. For 300,000 years, human beings have looked up at the night sky and built stories around that darkness. Stories of loneliness, of smallness, of a vast, cold universe in which we are a rare and fragile exception. Those stories shaped religion. They shaped philosophy. They shaped how billions of people throughout history understood the meaning, or the absence of meaning, in their own existence. And all of those stories were built on a foundation we didn't know was wrong. The night sky is dark because the universe has an age, and that age creates a horizon we will never cross. It is dark because space is expanding, and that expansion is slowly, patiently, endlessly stretching the light of every distant galaxy out of the range our eyes can register. It is dark because 90% of the galaxies in the observable universe whisper too faintly for our instruments to hear, until Webb began pulling them out of the darkness, one by one. 3 reasons, all real, and all pointing to the same thing. The distance between what exists and what we can perceive is far wider than anything we ever imagined. The next time you look up and see all that black between the stars, remember what is actually there. Trillions of galaxies, hundreds of billions of trillions of stars, an ocean of ancient light on its way to you right now, stretched, cooled, hidden by the very structure of reality, but still there, still arriving, still touching you in ways your eyes will never know.